Yeah, let's get started. Let's finish up. I think we'll finish it up as far as I remember. Let's finish up inheritance. That's very, very exciting. Well, let's learn how to do. So the setup from last time, what we were doing, right, is we noticed that when we've got like classes, it's all object oriented stuff. So when you have some classes that share features, share methods, share like the same kinds of data, like the name and the age were in common, right, between cats and dogs. The goal should be to package those shared things into a base class, into a super class, into a parent class. There's so many different ways to call it, but you put all the shared stuff there, and then you have cat and dog. You have your things that use the shared stuff. You have them inherit. You have them inherit from the base class. And just the fact that you put stuff up there, the stuff that's in common, does not necessarily mean that it has to be what was there. It doesn't have to be like, you don't have to stick to the animal versions of things. You can override behaviors as well. Just like this talk method. Like cats should talk differently from dogs. So we did that. Yeah, it was wonderful. And the very last thing we were talking about, let me copy in, I guess, stuff from last time. Let me copy in stuff from last time. To talk about what we were doing. So copy lecture 25's inheritance.cpp to here. And this is how we did it, right? We have the animal class, it's got the name and the age, and because we would like to treat eventually animals like their base class, and cats and dogs like the animals that they truly are, right? Put them together in a certain place. That's what we ended up doing. We ended up making a vector of animal pointers. You can either do pointers or references. You can't undo animals themselves because it cuts off the cat and the dog pieces. But if you have animal pointers, you can treat a cat pointer, because what is Victory but a dog pointer? Lonzo is a cat pointer, right? Ampersand Lonzo. That's a cat star and a dog star. You can put them in a vector that expects animal stars. So you can treat subclasses like their base class. That's wonderful. And when you say virtual, that was the last piece of today, we had to mark the talk method as virtual, so that it didn't just like default to saying animal noise, because that's what happened first, right? It went to, just by default, it gave you the animal version. If you want to treat your cat like an animal, it gives you the animal implementations of everything, unless you mark those implementations as virtual, which means prefer the subclasses version. That's all that means, okay? So that was where we left off. I hope that it makes a little bit of sense now that we're coming back to it, but that's what that was all about. And we said down here in the dog, inherit publicly from animal, talk override. You don't have to say virtual ever again. It's been marked in the base class as virtual. You say override, and then you get that version. So if I compile what we have right now, the fact that we did that gave us iterating through this vector of animal stars, treating each dog and cat like the animals that they were. Like the shared thing is still fine. That was up in the animal class, but the talk, we got the overridden talk methods. Beautiful. Lovely. All right. And so I think that's where we left off, and I think that is where I want to start today. Are you ready for that? More inheritance? Okay, so that was just like an overview. So virtual methods are wonderful. They do involve a little bit of overhead space-wise to make that happen. And so I'd like to teach you about a magical concept called a V-table, short for virtual table. And that's how it knows, like when you have an animal star, but it was really a cat, or really a cat, and you had an animal star that was really a dog, how it knows to get the dog's version of the code, get the cat's version of the code. There's a little data structure that's part of every object. It's pointing to a piece called a V-table. So for every class, a virtual table gets made if you have any virtual methods. So this is how this works. So, okay. Every class, when you have a class and you have virtual methods, it creates a data structure for that class called a V-table that points to that class's versions of those methods. Because what is code but something in memory too? You'll understand that more when you get to CSCI 45. But code lives inside of memory just as well, and that's where it's running. So every class gets a little V-table, and that method maps like names of methods. It's like a little mapping, like it's like a map data structure, a hash table maybe. But like animal gets a V-table because we have one virtual method in animal, a virtual table. And so it's got a pointer essentially to the code where the animal's talk method lives. Like it knows that there's a talk method, it lives at address 100. I don't know. That's the thing. So every class with virtual methods gets a vtable. So they all share it because it's like every cat is going to use the cat's version of the talk method, right? So cat's got a vtable. I guess it's lowercase. Vtable. Dog's got a vtable. And they all have like essentially a way to get to the versions of the talk methods for each of those classes, the ones that we've specialized. And so whenever now you make an object of a certain type, like you made an actual cat object, you said cat C or whatever, you did it right? What happens when you make a cat C? It's got like the name, right? It makes all the fields for everything. Like you got a name, an age, a favorite food, like all those things exist for cats. For every object you have those things, space for those things because they can all change. But in addition, every object gets a pointer to the vtable for that, for the type, for like the most specialized version of its type. So you get a vtable pointer, vtable PTR, let's say, and it's going to point to cat's vtable. And it knows that if you ever want to call the talk method, it's going to dereference this vtable, go to the talk offset of it, like index 1 or something, index 0 of cat's vtable, and call that function, call that version of the function. That's how it knows where it lives. And that implies that whenever you make a dog object, in addition to all the dog stuff, you say dog D, here's what D looks like. It's got a name, an age, and I forget the third thing that a dog... We gave it had a college, right? Name and age and college. It's also going to get every object that is a dog has a vtable pointer as well now. Secretly. So that virtual method calls work. And so it's going to point there, and that's how it knows to get the dog's version of the implementation for talk. Okay? So now, hopefully it kind of makes a little bit of sense what happens in this code down here. It's like go to the animal and say, hey, animal, call the talk method on yourself. Because that's a virtual method now, the way the talk method got called on that pointer, it's like, all right, it went to the actual object. Talk was a virtual method, so it followed the vtable pointer, and it got to that implementation. That's kind of how that works. All right, so that's at a very high level. You will maybe learn more about it if you go back to your CSCI 40 textbook. It might talk about that a little bit. It should in the inheritance section. But that's how the calls get made. You say you had a pointer to a dog. You said talk on it. All right, that was a virtual method. So it went and dereferenced the vtable pointer, went to the implementation for, like, it went to the address of the talk method in the vtable. That's how it knew to go to that one. And yeah, that works because like they all have that thing inside of it. Every object has it. Yeah, but it only works when you have method calls via references or pointers, because that keeps the cat parts intact, right? If you said animal A semicolon, you're technically allowed to do that. It doesn't have like the favorite food anymore. It doesn't have the college anymore, right? When you just say animal, and it doesn't know that the type is something else because you said animal at that point. It doesn't know that it's something more specialized. So if you forgot the star, for example, it would cut off the fact that it knew that it was a cat, that it knew that it was a dog. But keeping it this way, it's like, all right, it's just a piece of memory. Then the vtable exists in the same spot for any cat, for any dog, for any animal. So that's kind of how that works, if in a very high-level nutshell kind of way. Okay? Any questions about that? I don't really plan on testing you on the nitty-gritty details of the vtable, but I want you to understand kind of how it's working, at least. All right. So yeah, there's more. We're not quite done. I want to talk about something called protected. You'd learn more about that if you read about inheritance in a textbook somewhere. Not our textbook, it doesn't have that. So in addition to public and private, there's something in the middle. It's called protected, and it only makes sense to talk about it in terms of inheritance. It doesn't make sense any other way. So let me show you the problem, and then we'll get to it. All right, so let's say that it is Victor E's birthday. So let's try to make like a birthday method for Victory. Happy birthday. We want to do age plus on the dog object, right? Because every dog, scrolling up, There's a lot of scrolling I gotta do today. I'm gonna go back and forth. Every dog inherits from animal, doesn't have its own field called age, but the animal part of it has an age. Yeah, that's there. So I would like to do something like this. Hey, Victor, Victor E dot, I don't know, birthday. And then his age should be bigger now, right? If we say Victor E dot, like, get age, it should be bigger, yeah? So that's what we want. So let's make a birthday method for dogs. Only dogs can have birthdays, let's say. So I'll put it in dog, and something weird is going to happen. All right, so I'm going to say birthday. This is void birthday, age plus plus. Yeah. There's my method called birthday. It's part of the dog class. I should be able to do something, because I know I have an age member variable, right? It's part of the animal stuff. There it was. I should be able to say age plus plus and then call the birthday method in main. I wouldn't be showing you this if it worked. So there is a problem here. This does not work because age was inherited from animal and it was private in animal. You see the problem there? Private means only the class itself can see it and access it. That's what private means. That's not changed. When you inherit, when dog inherited from animal, it has a member variable called name, it has a member variable called age, but it cannot touch it itself because it's private from dog's perspective. You see that? It's not the same class. It's not the same animal class anymore. It's an inherited thing. We're not allowed to touch it. This is private from dog's perspective. It cannot see it like you could see it in the animal class. In animal, it's like, yeah, sure, return age equals new age. You're allowed to touch anything you want when you are the class itself. Your private things are allowed. You're able to see them. But anybody else, even somebody who's inheriting from you, you mark that thing as private, they don't get to see it. You got to give them access in some other way. So technically, we could say set age on ourselves. That was a public thing we inherited from animal, right? We could say set age and get age. That works for everybody. That was inherited publicly. But we'd really like to say age plus plus, right? We should still have control over the age member variable. Enter protected. That's what we should be able to do, okay? So public means this thing that you're having, this method, this member variable, everybody gets to see it, even the user, anybody who inherits if you inherit publicly. Private, we know, is visible inside the class only and not even to subclasses or derived classes is another name for that. Protected is in the middle. That's when you mark something, a method, a member variable, as visible to the class itself, of course, always, and all of its subclasses, but not somebody who makes an object out in main or something. That's kind of what we want for every member variable when you have inheritance. Usually you want to mark them as protected so that you can still touch them manually in any subclass. That would fix this problem. Does that make sense? That's a new access modifier that would give us what we want. All right, so let's kind of mark what's going on right now. Like we had our Victor E object, and what he had was all these things. I think PowerPoint lets me make straight lines if I stay there for a second. Do that. Yeah, that's very beautiful. Yep. That's so nice. All right. Victory had a name, right? And an age, but they were inherited. Age, if I can spell. And he has a college, and that was part of himself, right? That was the new added thing. So the name and the age parts were inherited from animal. These member variables exist because we inherited them, but that doesn't necessarily mean that we get to talk about them. We don't get to say their names. Unless they were protected or public. All right, so these pieces were inherited from the animal base class, inherited from animal. We cannot access them directly because they were marked as public, right? We can't access them directly while they're private. Sorry, unless they were public or protected. We cannot access these directly. They are there, they exist. We cannot access these directly without making them public or protected. Let's just say protected here, because that's the new idea. Without making them at least protected. at least. Something like that. That will solve the problem. All right, so let's go and mark all the member variables of the animal class, not as private now, but as protected. That's a new keyword. It's still in red for my editor. So now these are visible. We're able to talk about them in any subclass. Now these are visible to subclasses. They're always there, but now we can modify them manually. We don't have to like go through any public thing or other protected thing that gave us access to them in a different way. Like this is what the user gets. We're better than the user. All right, mark them as protected. So in theory, when you have an inheritance hierarchy, you should be marking all of your member variables as protected. That's usually the right way to go because it still disallows outside of the class. So like for dogs and for cats, like even their member variables, I should probably be marking them as protected just in case you wanted to make different kinds of dogs, different kinds of cat classes. So yeah, that's the thing. I'll just be lazy and keep them private for everybody else. But now, because I inherited age in a protected way, from animal. Now this compiles and now this runs. So Victor E gained a year of age. So now he's 4 and we printed that out. Okay, because he started out being 3. Does that make sense? What just happened? So protected is a way to get access to member variables that you inherited. You can say their name now. All right, and it's still keeping you from being able to do this. It's still keeping you from being able to say like Victor E dot age plus plus or something like that's still disallowed by saying protected. It's a protected member of the animal part of the dog class, and that just means as part of that. You can use it in the class itself or in any of its subclasses, not anywhere outside, and this is somewhere outside. So this is still not allowed. It won't compile. Okay, so that's great. That's what we wanted. So I think that's most of what I wanted to say there. Dun, dun, dun. So yeah, I think that finishes my inheritance example. Now you know it. Are there any questions about protected and why you would use it? Hopefully it's not too bad. So you now know why everybody in the 80s flocked to object-oriented programming and also the 90s. It's still pretty popular. It's everywhere, but there are new paradigms as well that have like stolen some thought from object-oriented programming. But it's still very, very popular. You still need to understand it because I think it makes life easier in different ways. So yeah, you now know about all the different features of object-oriented programming that everybody loves. The 3 main ones, the 3 pillars that object-oriented programming stands upon are called encapsulation, polymorphism, and inheritance. So you know all of them now. So encapsulation is the idea where you can just like mark things as public or private, like you get to see stuff, but the user does not. That's when you're hiding implementation details, and you're also like encapsulating. You're bringing things to. You're fusing data plus code. That's what classes give you, right? Public and private and protected now. They get to hide information from the user, the stuff that you don't want them to see, like just the nitty-gritty details are for you, the implementer, and the other stuff the user can just go without. All right, you get to show them as much or as little as you want to show them. You're encapsulating data and code together as well in classes. You're talking to these objects as if they're real life things. You're saying, go do this thing for me. Go have a birthday. All right, so that's encapsulation. That's just using classes in general and hiding information from the user. That's what that means. Polymorphism, you know that as well, but there's a bunch of different kinds of it. It just means many forms, right? So polymorphism is when you have like the same function or method working differently in different contexts, in different places. So there's a bunch of different kinds of polymorphism, and you know about them. It's just maybe you've never thought that they fall under some umbrella of some more generic idea. But there's 3 kinds. There's ad hoc polymorphism. I'm not going to test you on these terms. It's just when you have the same function or method working differently when you're giving it different types. So you know that like there's a plus operator, and it's called operator plus. You can implement an operator plus for your own objects. You know that it works differently for ints versus for strings, right? It does something different. And so you have the same name, but different forms of it, right? It has many forms, the plus operation. It does different things depending on where you use it and how you use it. There is parametric polymorphism, which is your templates. That's your templates. That's when you write something generically and it works the same no matter what. Like you get a bunch of different forms of the max operation just by having a less than operation too. Something like that, all right? So that's the thing. When it's working generically, regardless of the types involved, like making a length of a list for a parameterized linked list with nodes of any kind of data, type T data. You know that the implementation for list length just means like you're going to go and find where the end is, go looking for the null next pointer, right, and counting. So the implementation works for any kind of list you could possibly give it, right? So that's parametric polymorphism. And then finally, you got subtyping, which is a kind of polymorphism that is when you have different methods. It's like virtual methods. So that's when you use inherited things to perform different tasks. Like you get many forms of the talk function, for example. And that was us doing that. So that's polymorphism. There's a bunch of different forms of it. Some of them, a lot of them, have classes involved. And then inheritance, now you know about that, right? That's when you're sharing code, you're sharing functionality, data, and code itself between like a parent and a child class, maybe a grandparent, right, to a child as well, so that you don't have to like copy and paste everything all day long. So those are the 3 pillars of object-oriented programming. If you combine them all in cool ways, you can make fun programs that, in theory, are easy to manage and add to when you have new requirements. So yeah, now you know it. So those are words that you can understand now. I think with that in mind, what else do we have? I want to do that, and I want to do that. So yeah, let me give you, they'd take away my computer science card if I didn't show you this example of inheritance. This is like what everybody shows you. It's like, all right, let's make some classes called supervisor and employee and person, and here's the hierarchy. Supervisor is a kind of employee, and every employee is a person. Yeah. So that's a nested inheritance hierarchy where things are in common. Got all those 3. Those are the names of our classes. All right. So the most generic kind of thing you could be to represent inside of the code would be the person type. So the person class is going to have, let's say, like a name and an age. Every person has those things. And then an employee is a kind of person, right? So that you got an is-a relationship going on, don't you? Every employee is a person. Employee. No, I can't spell that. Employee. Every employee is a person, but it's got some other thing. When you're an employee, you get paid, right? So you get like a salary. And you have like an employee ID probably. Something like that. Got all those things. And then let's see what else. And then a supervisor is a special kind of employee, right? Who is also a person. So like at this level, you got another is-a relationship going on. You got supervisors. A supervisor is an employee. A supervisor is an employee. And what extra things do they have? Maybe they have like a list or a vector of all the employees, like pointers to the employees that they're supervising or something. I don't know. Something like that. Employees that they're supervising. So that's the hierarchy. And then you can also have some shared shared methods involved as well. Let's say that every person knows how to print themselves, like or at least turn them into a string to be printed later. Like there's a 2-string way to print a person, just like say their name and their age. Maybe we also want to update that, right? Because when you have an employee, it's going to inherit the 2-string implementation from person, but there's more things as part of an employee. Maybe we should add those when we're calculating the string version of that object. So let's override the 2-string method in employee and in supervisor to like make it in a cooler way that you can like print out the new stuff that makes that type different and weirder and cooler. All right. So that's the hierarchy. Are you ready for me to implement it? That's just the standard one that everybody likes to teach. It's like triply nested. It's helpful. So yeah, let's do that. Person, employee, supervisor. So, all right, I'm going to be lazy and do everything within the class again. So class person, what are we at? We've got some public things. And we've got some protected things now, right? Because we want them to be accessible to the subclasses. So every person, well, let's do the data stuff first. So every person has a name and an age. So I need string. So you got a string name and an int age. If you want to be specific, I guess you could say unsigned int age, because you could never have a negative age. But that's beside the point. So, okay, person, you give me a name and an age, and I will set those things. Empty body. And then we've got a toString. We've got a toString function that just like turns that current object into a string. So it returns a string. It's called toString. It's const. It doesn't change the object. It just uses the things. And let's say that it's just like, how do you turn a person into a string? It's got a name and an age. Let's like say the name and a space and then the age as a string. There's a toString function in the standard library like that. So I don't think I had to say that, but just for fun, I said standard : toString. You could have just said toString. Well, actually, I did, didn't I? Because if I didn't have standard : here, it would try to recursively call the toString that I'm defining right now, wouldn't it? So I actually do need the standard : there. Thank you, past me. So there. That's how I'm going to turn a person into a string. And yeah, I think that's it. That's the person class semicolon. Okay, and so I can make a bunch of people, but I'll probably just make employees to start. So, all right, that's the person class. Now we want employee inheriting from person. So class employee. Employee inherits publicly from person. So like keep everything as they were. Keep the public things public, keep the protected things protected. And every person has some public stuff and some protected stuff. All right, so what's the new stuff for employee? You got a salary, maybe has some decimals, right? So salary. And then an employee ID, let's say that's a whole number. Probably is a never negative again, so you could have said unsigned it, but that's beside the point. So for every employee, we want to be able to construct them. So every employee needs a constructor. So you want to make an employee, you better give me the name, right? Because every employee has a name and an age. It's got that from the person class. It's got a name, it's got an age, it's got a salary. You give me a salary to start this employee off with, and you give me an employee ID. And I'll go and I'll set all of those things. So we want to let's just use the person constructor to set the person bits of the employee. So we'll say that. So call the person constructor on the name and the age that was passed. That will set those parts. And then we'll set the new thing. So our salary, we'll set to the salary that was passed to us. And same with the employee ID. And again, we can have an empty body. So yeah, that's most of it. And now we want our own version of toString, and we want that one to be preferred if we ever treat anybody like a person. So I didn't actually finish this toString. I should have said virtual toString. Yeah, virtual returns a string called toString. It's a const method. I want to prefer the base or the subclasses version. I want the most specific version of this method, please. That lets us override it in the subclasses. So yeah, let's do that. Boop. So virtual string toString const again. Oh, sorry, you don't have to say virtual anymore. Actually, I don't think you're allowed. But it's now we're overriding the other one. Overriding that one. And what we want, essentially, let me get rid of this body. What we would like to do is attach the new stuff, right? Every employee has a salary and an employee ID. Let's add those to like the toString version of the person. It's like, well, we can call the base class's version of the toString method. Let me show you how to do that. So attach salary, because it did all the person work for us. We just need to attach a salary and employee ID, let's say, to the toString result for person, right? Because every employee is a person. You can call the person part of it if you want that version for a second. That's fine. And the way you do that is instead of saying, well, we're returning not just like toString, that would try to recursively call our own version of ourselves. I want to call the person's version of toString on this employee. Does that make sense? That'll turn the name and the age of this employee, because they got those into strings for me. So you say person : this is calling the person version of toString on ourselves. That kind of makes sense. That'll give me the name and the age space separated as a string. And then what do I want to add to that? It's plus a space maybe, and like standard : toString of the salary, plus another space, plus standard : toString of the employee ID. I think that's what we can return. So that is us attaching new things and adding to what it means to be an employee and how to print eventually an employee, how to turn an employee into a string. Nice. Questions about that? See how it's inheriting things, making it better? So there's that one. And then let's finally have a supervisor that inherits from employee. I'll just copy employee. Maybe that will make it faster for me. So supervisor inherits from employee. Supervisor inherits from employee. So it got the name, it got the age from the person part, because every employee was a person. And then it got the salary and the employee ID from the employee part. So, all right, every supervisor still has a string name. It has all these things, right? It has a name, age, salary, employee ID. And you can use the employee constructor to set all those other things. Give it the salary, because that's what it took, right? That's what it took to set those pieces of it. Because the employee constructor took all 4 of those things. Just give it all 4 to set those employee pieces of the supervisor. I spelled it wrong. There it goes. But we've also got new things for every supervisor. It's got like a vector of employees that supervisor is supervising. And for reasons, maybe those supervisors are themselves supervisors. So I would like to make a vector of not employees, but employee stars or employee references. Because just in case, like that employee that the supervisor, maybe you got supervisors all the way down, like a supervisor supervising some other supervisor. That should be possible. So I need to use virtual stuff. Yeah, so I need pointers. Pointers are references. So the new stuff for a supervisor is, let's do like a vector of employee stars. Those are the things that supervisor is supervising. I think that's how you spell it. Supervising, yeah. And so I need the vector type. Boop. So there. So that's a new thing. So you give me a vector of employee star called supervising. I'll set that. So this is going to get a little disgusting. Because really you should be passing vectors as constant references. So you give me that vector of supervising things, the things that the employee pointers that this supervisor is supervising. I will set my member variable to those. I'll copy them in, called the copy constructor. That's the new thing. Use the employee bits to set everything else, and then the supervising vector, set that to the supervising vector that was passed to me. So it gets a little disgusting and long, but I hope that you kind of see what's happening there. And then same with the toString, we're overriding it again. We just want to take essentially the employee version, because like every supervisor is an employee, print out their name and their age and their salary and their employee ID. Like that's the employee bit. So let's build up a string to return. String res equals the employee version of toString to start, because every supervisor is an employee. So that's this. Right now I've got a string consisting of the name, the age, the salary, and the employee ID of this supervisor. And then I eventually I'm going to return res. And then what I want to do is I need to turn everybody else, all these employees that it's supervising, into a string. Let's add those too. So let's add each employee that the supervisor is supervising to the string that we're outputting. Okay, so for every employee star E in the supervising vector, go and add it to the result string, and maybe like we'll indent a little bit. So it'll be like new line tab over, and then add the E version of its own string, E2 string. Like that's turning every supervised employee to a string, like tabbing them over so that you see all the things that supervisor is supervising. So yeah, I think that's what we want. And yeah, that's what supervisor is. It's got everything from employee to set the employee pieces, and then it's got the new thing. It's got the overridden string function or method. I think that's what I wanted to say. Any questions about that one? All right, so I've got all these things. Let's make them now. So down in main, let's make some employees. I can be an employee. My name, I got to give a name, an age, a salary, and employee ID. So name's that. I am 33. My salary can be pi every month, $3.14 a month, and this can be my employee ID. And then maybe the school hires my cat. His name is Lonzo. He is 5 years old, and he makes so much more money than me because he's cooler. Let's say he makes $1 million, and he can have the next employee ID. Okay, that's another employee. And then let's have a supervisor. So a supervisor, let's have Bill Kearney, the other computer science professor here, be my supervisor. So Bill, I'm not sure how old he is. He's at least 34. And let's say that he makes $10 million every year because he's supervising people. He's important. And he can have, he was here before me, so he's got to have maybe the ID before me, let's say. And every supervisor also needs a vector of employee stars that they're supervising. So let's say that he's in charge of me and my cat Lonzo. All right. So there's a supervisor. And then we can ask them to print themselves. So print myself as a string. Turn myself into a string, then print that. That's what I'm doing. And then Bill. So there I am using it. And let's watch it work. We're getting all the new versions of everything. It should compile. It should run. And then here's the toString methods for employees, print out everything. And then for the supervisor, you get the supervisor's employee bits printed out. We handed that off to the employee version of toString. And then we tabbed over and we printed out all the employees that supervisor was supervising. Lovely. Yay. So yeah, I think that's what I wanted to say. You got your person class. That's the base class. Employees inheriting from person, tacking on the salary and employee ID. You can use the person bits to make your life easier. And then same with supervisor. It's from employee, start there. Use the employee bits to make your life easier. Yay. Okay, and then you can use it. Any questions about that example? That's just like the classic example that everybody likes to give when they're teaching inheritance, because it gives you a couple base classes, a couple super classes, and you see how they're all working together. A virtual method. Yeah. Okay. Yeah, so I think there's not too much more that I want to say. I want to teach you about a couple different ideas, and then we're almost to the end of them. So I think I don't need to say any code for this one, because you'll get the idea, I think. There's a concept of inheritance that we're learning about. There's also something called composition that can trick you into thinking something else. Sometimes you want to reach for inheritance, sometimes you reach for composition. You've used composition before. I just want to spell out the difference now that you know both terms. So inheritance is for when you have an is-a relationship going on. You should have shared stuff. So like a cat is an animal, you should reach for an animal base class. Right? And then animal is the base class, cat is the subclass of animal. Same with employee. Like an employee is a person. You should have a hierarchy. Person is the base class. Employee is the subclass. When you have those is-a relationships, you have superclasses and subclasses going on. Same with cars. A Jeep Wrangler is a car. All right, that's what my mom drives. So that is for is-a relationships. You use inheritance to take the shared things, and you don't reinvent the wheel. Composition is for has-a relationships. Composition is when you make little member variables. That's when you put stuff inside of things, all right? Composition is when you just you make a new field of your class. You don't inherit from anything. So like an animal has a name, that's a member variable of every animal now, all right? A node has a next pointer. That should be a member variable. That should be a piece of it. A bicycle has a rear brake, for example. You don't inherit from rear brake or anything like that. You're just going to add that as a new field. That's a piece of you you're going to hold on to, all right? They're all parts of your object. Not the whole thing. It's not like another more generic version of it. It's a part of a whole. Yeah. So that is the difference. Both terms are about sharing stuff, but the sharing is completely different. I hope you see. All right. So those are two terms that you now know. So let's see. I don't want to say that. So yeah, you make an animal. Dun, dun, dun. You know that you can inherit from animal, get all the pieces. But every animal has, your animal A object, it has a name and an age. It's composed of a name and an age, you can say. Okay? And then like you make a bike object called B. Every bike should have a front wheel, a back wheel, a front brake, a rear brake, handlebars, a chain, stuff like that. That composes a bike. Those are pieces of it. Those should be member variables. You're not inheriting from the chain class when you're making a bike. You're not inheriting from the handlebar class. You're putting one in every bike object. Okay, so I hope you see the difference. You just got those two terms now. You're going to reach for one or the other depending on the problem at hand. Okay, yeah, I think that's what I wanted to say. Any questions about that before I show you one last thing, one last piece of inheritance that we need? It's going to make it easy for us to start our final lab. So we need this last topic. It's called abstract classes. All right. So this is when you make a class. An abstract class is a class that you cannot instantiate. So I will show that to you. All right. So an abstract class is a class that you cannot turn into an object. So you can't for example, you probably never want to make an animal object by itself, right? And have it say animal noise. You probably never want to make an actual animal object. You want to make a cat object. You want to make a dog object. You can force that to happen, force you to never be able to say animal A. Like you can make it so that you cannot do this and have it not, and it won't compile. You can make that happen because you probably don't want that. You just want to inherit the pieces of animal, right? That's kind of what you want. So if you have an abstract class, the idea is you cannot instantiate. You cannot make a variable of that particular abstract type. So if you had an abstract class called abs, you're not allowed to do this. Can't do this. If you mark it as abstract, and I'll show you how. Some classes are just good to be inherited from, like the animal class. It would be a great candidate for being an abstract class. Things that you don't want to have be their own objects, but you want to have them be superclasses of things you can actually make. All right. So an abstract class is a class that can't be instantiated, but it is the superclass for at least one subclass, and it specifies it's giving a blueprint for how that subclass needs to exist. All right. So the way that you make in C++, what it's called, the way that you make an abstract class is you give it at least one thing called a pure virtual method. This is very, very technical and weird words that they came up with, I know. But the second you give one of your classes a pure virtual method, that is a virtual method without any implementation, that's what it really is, then you have a class without code, and now you cannot make, you don't know what to do for that method if it were ever called. So that means it marks it as abstract. That's beautiful, all right? So a pure virtual method is a virtual method that you declare, and you technically define it. You set it to 0. That's how you give it something, but you're saying that it doesn't have a real method. It doesn't have a real implementation. It's not really implemented in that base class, and that forces... The second you say this, the second you make a foo method, you say virtual void foo, you say equals 0. That marks it as pure virtual. It has no actual real implementation of this part, in this part of the class. You say equals 0. Wonderful. And that's now forcing every subclass to give a real implementation for that method. Does that kind of make sense? The second you say it, if you're going to inherit, you are forced to give something real if you want to instantiate that object at that point. All right. So any class with one or more pure virtual methods, that should be plural, is abstract. And the way it works, the way you give it an implementation but not actually give it an implementation, is you say equals 0. It's weird. That's the syntax. All right. So the second you do that, you just kind of said that the base class has this thing, but you cannot make any of those objects of that base class because you could not call this method on that object. It does not have an implementation. It would not compile for you to do that. But you've marked that that method exists. And so any subclass, if you want that subclass to be instantiable, right, you better give an implementation. You just marked that that exists for everybody that you could possibly use. So animal could be a good candidate for that. You just mark the talk method on animals as pure virtual. That would be great. A simpler example is just let's have a class that knows how to print stuff. That's a good idea, I think. So here is a superclass that marks the ability that somebody has a printing method, because that's kind of what an abstract class is doing. It's marking the fact that a method exists, but it does not have an implementation. It's like anybody who wants to implement that then you're good. You could use it. All right. So let's try to make that an inheritance hierarchy. So I'm going to make a superclass called canPrint. You inherit from that if you know how to print something, how to print yourself, turn it into a string. So the way you do that is you say you have a pure virtual method called something, virtual void print, I guess is what it would be, right? Virtual void print. And then you say equals 0 semicolon. Boop. That marks it as pure virtual. So print is our pure virtual method inside of the canPrint class. And the second you say that, you cannot make a canPrint object because it does not know how to print itself, which is kind of ironic. But the second you do that, you know that anybody who inherits from canPrint and you can actually make an object out of, it must have implemented the print method. We know all derived classes that you can actually make objects out of, all usable derived classes, all subclasses, derived classes must have a print method because it's inheriting this. It's like inheriting the name. It's inheriting the blueprint. So we can make like maybe a class that knows how to print an int, right? Like an int printer. I know this is kind of silly, but it's a good example, I think. And you can make another class called string printer that knows how to print a string. That's maybe its member variable. And the second you do this, the second you inherit from canPrint, that marks that you have a print method. And if you want to make an int printer object or a string printer object, you better actually give an overridden implementation, actual code, actual body for that print method in each of these. So that's what an abstract class does. The second you know somebody inherits from this, it's marked that everybody has a real implementation of any pure virtual methods. Okay? It's very technical and complicated. It's very technical, but hopefully it'll make sense, right? Hopefully it makes sense when I show it to you. So, yeah. Are we ready for the code part? I think that would probably help. Any conceptual questions before we go there? All right. It's going to be an abstract class. So, so I'll say class canPrint. If you inherit from this class, I'm going to give it a virtual void print method equals 0. Second I say that, I cannot make any object called canPrint. So anytime okay, let's do it in this order. So this is a pure virtual method called print. All right, this is a pure virtual method. It marks canPrint as an abstract class. The second you do that, you cannot say this, canPrint C or something. Because canPrint is abstract, the whole reason that's not compilable is you can't say c.print. It has no code for that. It does not know what you're trying to do. So this won't compile. I cannot make an object when it has a pure virtual method. Can't use that class, all right? The whole point is that I inherit from it. So anytime somebody inherits from canPrint, we know, and we can actually instantiate them, we know that they have a print method that they implemented themselves. That's what that marks. So if I want, let's have like an int printer, class int printer. It inherits from canPrint. That means it has a print method and it knows how, like it actually says it does something, it has actual code. So let's just say every int printer has an int I, and here is how you print stuff, like void print override. Actually override the print method, give it an actual body, and like how do you print your int I? Just do that, something like that. But the fact that it inherits from canPrint means that it has a print method. It means it has a print method, And if you can make an int printer object, that means that the print method has been implemented. Somebody gave it a real implementation somewhere. All right, so there's int printer. We'll do string printer just for fun. I need the string type. And then how do you print your string s? You say cout_s. Okay. So that's our hierarchy. Does that make sense so far? There's the hierarchy. Now let's talk about what kind of objects we can make once we've done that. You see what's going on there? So pure virtual print and the can print method, but we got int printer and string printer inheriting from that, and we're forced to override if we want to make an int printer or a string printer object, because we can't right now do this. Can't be like can print C. That will not compile. But you better believe we can do this. We can say now int printer IP. IP's int is 42, and you can be like ip.print. That totally works now. Yeah? That for sure works, and that's going to compile because we got a real implementation for the print method here. Look at it. It's wonderful. It has code. Same for string printer. We could do that. It is instantiable. It works. SP. The string inside of it can be I'm on. And we can ask SP to print itself. That is going to work just fine. Does that make sense? The fact that they inherited from that abstract class called canPrint means that you know that they've got a print method that they've actually implemented, and it has real code. That's what it means to be able to instantiate an int printer object or a string printer object, to actually make a real one, because you couldn't do it for the abstract class. It didn't have code for the print method, but these do. So you've marked that that print method exists by having this particular kind of abstract class. Think about that in terms of animal and talk. We probably should have done that for animal and talk. That would have made sense. So that's forcing everybody to give it a real talk method. Okay? That's how you do it. I think that's most of what I wanted to say. So yeah, if you understand the hierarchy, kind of why you would want this is like, now you better believe that you can make a vector of canPrint objects, canPrint stars, you can treat these things still like their base class, because they're all canPrint things, right? Things that have a print method, aren't they? And then when you can call it because you know that it was some subclass that actually implemented print. So you can treat them like the base class, even though that base class was abstract. That's beautiful. So equals star IP, ampersand IP, ampersand SP, and so I need vector. So I can treat them like their abstract base class still. Just, it's fine, because I'm going to call methods on them. I know if there were any objects that I can actually make that I can treat like their base class, really did have the print method implemented. So I can say like v at 0, arrow, print yourself. V at 1, print yourself. We're treating them like canPrint objects, but now I just see it twice. That's the new stuff. We're treating them like canPrint objects, and that's okay. Even though that's some class that I can't actually make an object out of for real, I know that I've got real base class objects. Objects of some subclass, excuse me. Lots of terms floating around. Like, all right, this thing is some sort of canPrint object that has a print method I can call. That's what the type kind of meant for this one. All right. I hope that makes a little bit of sense. Any questions about that? It's a little complicated, this abstract class idea. It's like you mark a method as not having an implementation here yet, but just the fact that you have it means that your subclasses have to give it some real code somewhere. That's a way to mark that. And so it's abstract. It's just like a blueprint. Here are the names you got to give me eventually when you make a subclass with actual meat involved. Okay? And why you would want this, hopefully it's a contrived example, I know, but something that we could have done is like, you could have inherited from multiple classes. Other languages do this in different ways. Like Java probably has a better version that's called interfaces. Like CanPrint probably should have been what's called an interface in Java, but you're forced to use abstract classes in C++. Here's a good reason to want to do that kind of thing. Employee could inherit from person. We know that already. We did that. But you could also have employee inherit as well from CanPrint, right? Because that would force it to have a print method. You can treat it like that, right? It could implement like maybe you can make a program that kind of like shows an employee's ID card or something. So like you can print it on you can draw it on the screen. You can draw to the screen. So you can inherit from a bunch of different classes, and some of those can be abstract classes, just kind of forcing you to give an implementation for how to do that thing on that class that's inheriting from it. That's kind of nice. So yeah, you can inherit from multiple classes at once. That gives you a bunch of different shared functionality. If you inherit from an abstract class, it's forcing you to have a method, forcing you to implement those things. You have multiple pure virtual methods per abstract class, of course. That's a thing. So, yeah, I think that's most of what I wanted to show you. Any questions about that idea before I give you a question? I want you to try something. So, here is your question. Let's say we would like to use inheritance to make trees. We'd like to make trees, and we'd like to use inheritance to mark that those trees are non-empty trees. Like they can never be empty. All right? So to mark the fact that we can make a tree that's never empty, so we don't have like null for meaning emptiness. So that means we'll make like a base class called tree node. Right? We'll make a base class called tree node. That's like a node of the tree, but it's never empty. It's always going to either be an internal node or a leaf node. Right? Every piece of a tree, either the root, right? The root could be an internal node or a leaf node, but it's never empty. And every internal node can have children, right? Internal node can have children. But maybe it's forced to have always a left and a right child. Because the only kinds of nodes you can have are more internal nodes or more leaf nodes. Yeah? So that would force you to make, I guess, complete trees always. So my question for you is what types, so like internal nodes and leaf nodes are the two kinds of nodes that you can actually use. Like tree node should be like an abstract class maybe, abstract base class. What types would you use to make this tree, that exact tree? How would you use these types to make that tree? And then also, what fields would you put in each class? Like what would belong in tree node? What do they all have? What would belong in internal node? What would belong in leaf node or not belong in leaf node? So those are things, okay? Those are things that you can do. Where like the goal for making fields and methods maybe even, your goal is to traverse that tree. Like you still want to be able to traverse it, but you don't just have one node type anymore. So my question for you is, what would you put in each of those types? If you want this kind of inheritance hierarchy, and how would you build this tree? You don't have to write this down anywhere. You probably have to draw something, like maybe break out paint or a piece of paper. But I want to give you guys some time to think about that hierarchy and how you would do it. Because you see that there's no way, like if you mark these as the only classes that are part of could be tree nodes, you now cannot have an empty tree ever. That's interesting in itself. And then how would you like make these types to enforce that fact? So that's my question for you. And please give it a try. I'll give you a few minutes to think about it. Maybe draw a picture with yourself or some with the people sitting next to you. You don't have to submit this. I just want you to discuss. Thank you. That we should have a kind of specification that we say like a goal. It's like, so what do they have in common? What should go on that should go? If we have like a goal that's like you can get to like it's all in common. What would you do? Like each tree node and
Or would that be
I guess it's specified that they're all no, it's one very they're always
yeah, you're right. I don't know, my brain interested in that.
I think it's because it's like it's specific.
Yeah, my brain that's true. Yeah, definitely internal picture.
The internal node has but what would be the difference between the tree node?
That's something. They all have parents. That one is down. I guess the I guess however you go, but also how to put the sister.
Another minute or so, and then I'll show you my thoughts.
I think the only thing we have now is from abstract class.
Yeah, so things like that.
So it literally just be the same thing, so
Yeah.
it's not abstract. But I guess there's value in that. But like, it's
You could just have a tree that would be
yeah, and not have a third one.
All right, that was my timer. Let us come back together. Let's see how this might work. Can I copy and paste that? That would be great if I could. Let me attempt. So let's see. I think maybe the tree itself would make the most sense. So I want to make the tree 2 as the root, then 1 and 3 as the left and right. So let's see. You better believe that 2 is an internal node, right? It's not a leaf. It has children, yeah. And that's probably the difference between internal nodes and leaf nodes. Give me an internal node, that's the 2, and it should have a way of getting to left and right children, right? And then the other guys, those are both leaves. The 1 and the 3, those are actual leaves. So you make them as leaf objects, wouldn't you? Cool. Leaf 1. So that would be the way the tree looks for sure. You don't really have any options there. But now the question is, let's see. What do we put here? Can I copy it? Oh, no, almost. Yeah, now let me try copying and pasting this in a different way. Just the drawing, please. So, the idea of what to put where is an age-old question. I guess what they all have, right, is data. That's for sure what they share, yeah? So let's put that in tree node to star. I think that's a good idea. So, dun dun dun. For the data of our tree node, we got the one int, right? That can be called data. It's an int, okay? And then now the question is what to do about everything else, because the idea of internal node, you should be able to go right? Go left and go right, but like I've got more room to the right, so I'll draw over here. Going right, for example. Right. Right could, if you want to use pointers, that's fine. Right could point to either, right, an internal node or a leaf node. It didn't have to be a leaf here. It could have been a bigger tree, right? It could have been another internal node with stuff like that, yeah? So what must be stored in the right part of your internal node is not another internal node or a leaf node. It must be a tree node. Does that make sense? You have to do it like that. Or a tree node star, something like that. Tree node star. So right could point, because you don't know which, right, could point to either internal or leaf. And so we better use the base class there, because we're not sure which. If I could write the right letters, that would be great. So that's a cool idea. And that kind of forces some things upon us. So let's work on the data for now. Leaf doesn't actually need any extra data. It just has that in, right? That's all it needs. Internal node has some extra data it needs. It needs the ability to know what's to the left of it and to the right of it. Whee. Maybe you should make this actual nodes. I don't know the right way to go about this, because if you put a pointer, then you could kind of you can turn an internal node into a leaf that way, but that's beside the point. You can make methods that force things upon you, but let's have left and right for sure. Like, you need to store who is to the left and who is to the right of you in some form, but they got to be tree node stars, don't they? Because we're not sure if it's another internal node to the left of me or another leaf or a leaf node to the left of me. Same with the right. Tree node star. And so we need those things, and that is the way that we can eventually go left and right. But when we go there, right, we're going to go to the left and see what's there, and it's going to be a tree node star, and we have no clue if it's a leaf node or an internal node, because we're looking at it from the perspective of a tree node, right? So we're going to have maybe like a tree node star iterating through this tree, and we're not sure if what we're at is an internal node or a leaf node. We can't even know if we can go left or right or not, but we need that ability, don't we? So you should be putting then, we're going to need some extra methods up at tree node, because we're going to treat everything like a tree node. What should they all know? What should they all be able to say? They should be able to probably say, what are you going to say? Yeah, the type, somehow. I think maybe the easiest way to do it is like have a bool method saying like, was this a leaf or not? Something like that. Like, is this tree node a leaf? Is it a leaf? Like, that can be a method that you could then go and implement. That can make it a virtual, a pure virtual method making tree node a base, an abstract class, excuse me. And so like, is leaf would return false for internal node and return true for leaf node. Like, that could be that implementation. Like, is leaf. The implementation of that guy is going to be like, return true. Return true. There. That would make sense. And then also, we need the ability, if it was a leaf, you can't go any further. But if it was a leaf, you need an ability to go left and go right, actually, from the perspective of a tree node, right? Because you're not sure when you went left, like, okay, it wasn't a leaf, but I'm still looking at this as a tree node star. You can't like change that fact. So let's have a method for go left and a method for go right. Yeah, I hope that makes a little bit of sense. You need those things. Those are the things that let you treat a tree node like each piece of the tree. Like these are what give you access to the underlying features of whether it was an internal node or a leaf node. Okay? So I guess a good implementation for like go left and go right on leaf nodes is you don't want it to do anything, right? You have to give some implementation, but you don't want it to do anything. Excuse me, thank you. So let's say like go left, for example. And this is just me making stuff up. Like there's probably a better way, but like this is one way to do it. So like go left should probably like return null for a leaf. That would make sense. Because there's nothing. There's nothing there. But go left on an internal node should return whatever is actually in the left member variable. Return left. Like that. That's the stuff you'd put there. And like, is it a leaf? For an internal node, you return false. So that you know you actually can go left and go right and call those things and get actual stuff out. Return false. Oh, sorry. Yeah. Return false. Something like that. And then maybe as you're making internal nodes, you can, as you construct it, you can force and make sure that left and right, like at least one of those is not null. Like that's part of the constructor or something. Like you can do that. That is possible. So yeah, I hope that makes a little bit of sense. Like left and right, you still need access to them. That's the new stuff. So the new data for internal node is left and right. Leaf node doesn't need any new data. It just has that data inherited from the tree node part. And those are the ways that you could treat everybody like a tree node and still do what you needed to do by calling those methods that we put up in tree node. We noticed we needed them. Okay, so that's a little weird and philosophical. There's probably other ways. There's definitely other ways to do it. But I hope you see like the power of that. Like it forced something on our trees, the fact that they could never be empty. And that could maybe be useful to us. Okay, so I think that's a good place to stop as far as new information for your brain goes. Are there any questions about that example or anything else? Because that's my last slide of the day. Yeah, so that's inheritance in a nutshell. It's like you're sharing stuff from, you notice that you have some stuff in common, or you want to force something upon someone. That's what abstract classes are for, right? And then you now have a parent class and a child class relationship going on. So that's how that works. Now you know about it, and we're going to need that for the last major topic of the class that will influence our last lab, and we'll start that on Thursday. All right? We'll also talk about the test on Thursday.